Hello everyone. This is a tutorial about logic and problem solving with Prolog. And the copy of the slides that I will use is available at my GitHub repository. If you want to go a little bit asynchronously, either forward or backward to them, just get them from this Prolog tutorial repo. I will let you see if you want to do that and then start. We have 76 slides and about an hour and a half, so we'll go a little bit faster on easy things, but I'm assuming basic familiarity with the language at this time. All right, so that's a bit of an overview. We go over a little bit over the history of Prolog, the basics, look at how Prolog works in some detail, neat language constructs, some extensions, and Prolog as a problem-solving tool with some moderately kind of mid-level and then harder problems in the final round. After that, I will show you a simple neurosymbolic computing technique that involves Prolog. And then, of course, our conclusions and suggestions for the next learning steps. All right, well, Prolog at 50, forever young, and indeed, what is happening is that Prolog is coming back quite a bit. Part of it would be that is maybe a side effect of the new AI spring related to deep learning, but Prolog's ratings are pretty good compared to all those very neat languages, and that's the TOB index, which is a kind of beauty context for Prolog. So to get to the history a little bit, it originates from, I would say, two original motivations. Alan Kolmar wanting to do some interesting natural language programming with grammars, and then Robert Kowalski wanting to express algorithms and the computational aspects of computer science, in fact, as logic plus control. So write it down in logic and then have a little bit of extra annotations to control it, and of course, an execution mechanism. So Prolog is a subset of first-order logic. It's the Horn clause subset of it. The key difference there is that in the case of Prolog, we do not have disjunctions in the head. We have a single head term here, a predicate. I didn't put variables and more complicated notation, but this is the key difference. With that in mind, Prolog is computationally quite effective. The underlying algorithm is called SLD resolution, and it uses a very important element, which is Alan Robinson's unification algorithm. Multiple answers will be written, not just one, like the usual functional programming setting, and that was called non-deterministic execution, but in fact, it's just a stream of solution that's coming out. The new derivatives over the history, constraint programming, satisfiability solvers, answer set programming, and as a common thread here for the later ones, they exploit fast execution of propositional logic, and there is a grounding process from the Horn clause logic and even sometimes richer one to execute in reasonably accelerated way some specific problems. But Prolog is very general purpose, and of course is a Turing-complete programming language, founding member of the declarative programming family. All right, let's start with the basics of Prolog. I will show you here a little graph coloring problem. I have a set of edges. They are expressed as compound terms here. Of course, our variables will be distinguished from constants. They are uppercase. Those are predicates. There are constants, including the empty list here. And to express this algorithm, all we have to say is that for each of the edges of the graph, the two ends should have different colors. All right, so let's then take one color for each of the ends of the edge, and take one color would take one from a list. This is a list pattern. And then the tail of the list is what remains here. Or you can also iterate and not take the first one here, skip it, and then take it later from that list. So with that, you express, in fact, the multiple solution situation in Prolog, in which more than one color can be picked from a set. With this very nice recursive predicate recursion will be everyone in Prolog, and this is the result of executing the program with the edges colored, in this case RGB, right? Very simple coloring. Here you will see also multiple solutions coming out, and that's a common notation in Prolog. This is how you start SWI Prolog, which is easy to download for all platforms. And here's how you consult or load a program in memory. And then that's the prompt of the read, eval, print loop in Prolog, the REPL loop. You type something, and then multiple solutions come out. Here I'm using also some write statements to print them out in a more orderly way, but if there are variables, Prolog will just give them bindings. So that's the very short splash into Prolog, in case you're completely unfamiliar with it. Let's consolidate a bit more on that. Well, variables again, uppercase, constants lower, unification is transitive equality. If x is a and y is x, then y is also a. Equality denotes unification, and you can try out terms to unify. When you have compound terms, so terms like this one and that one here, then you have to go and unify each of the arguments. You can express that as a recursive algorithm. When you have clauses, they could be of two types, facts or rules. If they are facts, then Prolog will just look, in the case of this rule here, when you have a of x and you are looking for it, then you would alternatively unify a of x with all of those facts. If it's another fact here, that once you get a binding for x by unification, then agreement needs to happen between that and the x here. So only those values of b would qualify that match one of those values of a. This happens sequentially, of course, and this is the prompt in which you launch C of R, and then the solutions come out, R0, R2, and R3. R0 comes because this particular predicate C is also happy with C of 0 as a fact, and it infers by borrowing from A and B what A and B agrees on. So that's the execution mechanism, of course, in a nutshell. And let's now look at how we model something like propositional logic in Prolog, and introduce one of the control structures, which is the cut. Well, we want to model truth tables. Once you have truth tables, of course, you can express satisfiability as a formula that evaluates to 1 at least for one value of x, and then you can put a cut here saying, I'm happy with that, I don't want more, it's satisfiable if it has at least one solution to which the formula evaluates to 1. A tautology would be something that should not evaluate to 0 at all for any x that would be one of the possibilities in the truth table. So how we describe the truth table? We collect all the variables that occur in a formula. We write this little eval predicate that descends recursively on the structure of the formula. And then if we find result are here that could be a 0 or 1 to represent truth and false and truth, and then we write it out. We fail so that this iterates over, and then we say true when we finish. So the recursive descent for evaluating a formula, where logic variables represent actually our terms. Well, if we have a variable, we don't know yet the value, then we say a cut here. We don't look at any of these anymore. That's the semantics of cut. And then we pick a bit, which could be 0 or 1. And then we have multiple bindings for a variable. Well, multiple means 0 or 1 in this case. If it's already bound and an integer would recognize it, again, a cut here, then we are happy with that and just bind the result to that via unification. So that's a typical pattern to do case analysis in Prolog. If you have a conjunction that you want to evaluate, you evaluate all the parts, and then you go back, to a table that tells you how conjunction works, in particular that if both are true, then R should be true, and so on for disjunction and all the other Boolean connectives. So that's how you emulate Boolean logic in Prolog. Of course, our slides contain links to the code itself. At any time, you just click on that, and here is the complete code with more details if you want to see that. All right, let's see how the truth table executes. Here is A implies B implies C. Implication is right associative. Then you would have here the input values, zeros and one, all the combinations, 2 at n total, and here would be the values that come out. You can test for satisfiability, and you can test, let's say this one is a famous formula, Peirce's law. If this is a tautology or not, it would tell you that it is. It's one of the axioms that actually, if added to intuitionistic logic, you would turn it into classical logic. So it's an interesting one. We can detect that it's, of course, a classical tautology in propositional logic. So logic variables are very nicely used for binding them in various ways and then exploring all the possibilities. That's an advantage of relational programming. But Prolog also works very nicely with richer data structure, in this case with lists. Famous append predicate, if it's empty, then you leave the second argument alone, you return it as is. If it's a list pattern, head of the list, tail of the list, and then more, then you keep in your hand the head of the list first, you append the tail with the other guy y's here, you get z's, but that then you put back the head of the list so that you reconstruct the list as you go recursively. Again, simple recursion, but magic happens with append. Member, for instance, can be expressed in terms of append by just saying, well, if x is somewhere on the list, then x is a member of the list. And to say it is somewhere on the list, you can say if you append something that's before x, and then x followed by a tail here, something after x, underscore means you don't care about that particular value, then this should be x's. So this works in generation mode and also in just checking that something actually belongs to a list. Similar pattern for subsets, two possibilities. Either you add an element or you don't to the subset of the tail of the list. 2 at n, because the two possibilities, either you add it or not. A very simple quick sort. You take the first as a pivot. You find all, and that's a higher order predicate in Prolog, find all the y's such that y is a member of x's, and it's smaller. You collect the little ones, then you find all the big ones, and then recursively you do quick sort on the little ones. You get the first ones, quick sort the big ones, you get the last ones, and then you put it all together. You append the first, the pivot in the middle, and then the last, and then you get the result of quicksort. And here is how the execution goes for append. You can see that append works reversibly, actually, and any combination of known and unknown elements on any of those lists, when it's meaningful, will give a result that unifies the corresponding components on the three sides here. This is an example of our emulated member. They have underscores because they're built-ins, and I am hiding. I don't want to clash with the names that are standard in most Prologs. And this is the execution of subsets, and this is the execution of quicksort. So that was our very quick immersion in Prolog. So now let's look a little bit in more precise details how Prolog actually works. Well, unification is the most important thing that handles our information exchange between goals for which we want to find bindings and clauses in the program. So unification works recursively, and cycles are forbidden. That's a very important thing, because otherwise you get either crash if your Prolog doesn't manage cyclical terms, or logically unsound consequences if you insist that all the terms in the resolution process should be cycle-free. The recursive descent, again, combines all the arguments one by one. So now how this actually works, here is a small emulation in Python. Of course, we use a stack to eliminate recursion as well. The first step is to follow variable chains until you get to either a constant or an unbound variable, which some implementation mark it with a known in Python or null in C, or a circular loop self-reference of the variable itself. So after you dereference the two, you start with them in reverse order to pop them in the right order from the stack. Then you do a bit of case analysis. If it's a variable, the first one you bind it, and you have here a dynamic list in Python, a dynamic array that's called trail. It's an undo list, basically. If you want to clean up the bindings that you made, you can undo them by going over the trail and putting each variable back to its free state. The same story for x2, and then a case analysis here to see if it's a compound term, which can be represented by a nested tuple in Python. It's almost a one-to-one mapping between Python and Prolog in terms of Prolog terms on one side and nested tuples on the other side. So if is x1 a compound term and x2 also a compound term, then you will do more case analysis here. But if it's not the case, because they happen not to be not to be equal, then you have to return false here. And otherwise, you make sure that the arities of the two terms, which is how many arguments they have, are the same. If not, you return false. Otherwise, and here you go backward, because they are reversed on the stack, you would put them all on the stack so that when you go back here, while the stack is not empty, they get unified. The one corresponding to the left term first, and then the one to the right. So the same way as we explain it is what the algorithm emulates here. All right, that was unification, and now we have a two-clause meta-interpreter that would explain you inside Prolog how the execution mechanism of Prolog works. Well, let's look at it right away. These are my clauses. I have a very simple addition algorithm for unary arithmetic. Adding 0 to something is the same thing. Adding the successor to something means the successor of the result. If I just add x and y to give me z here. What's special is that I use a so-called difference list. The tail of the series of elements here is unbound. That allows me to just bind it, and then in constant time I am concatenating to the list. So that keeps open the tail of the list. Also, it's very useful to have that because the head of the list is easy to add elements, of course, but the tail, unless you work with difference list, would require an append, and that's computationally ineffective and also ugly. So you would then, with this different list representation, write a meta-interpreter. You have a list of goals at a given time that you want to execute. You start with the first one here, and then you go recursively. So what you do here, you look up a clause that matches the goal. By putting the same variable here, you actually trigger a search over the available clauses. And assuming that a match happened, the body of the clause, which is a difference list, will be simply extended with the list of remaining goals, and then that extended body will be further interpreted until the stopping condition, the success condition, empty list would be reached. With that, you generate all the solutions, and indeed the meta-interpreter working for us quite nicely here with a simple goal that represents the goal is one of our clauses. In fact, to keep it simple, add 2 plus 2 here gives a result which is 1, 2, 3, 4 in unary arithmetic. So the meta-interpreter basically works as you can see in this example. Of course, you can do it in Python, very small skeleton of interpreter. The code is at our site, the tutorial site, and you can run it in Python and actually get a little bit deeper in the execution mechanism. But the way the interpreter goes is very simple. You have an inner function called step here. You recursively apply unfolding. Unfolding is what I showed you here. Basically, when you unfold a clause, you replace one of the goals with an extended longer list of goals coming from the body of the clause, right? And that happens if the unification works. Undo is another little function here that unbinds variables when you fail or when you want to go further and give a chance for other bindings. You start with an empty trail. If your list of goals is empty, like in the previous page in Prolog, you yield a goal. Yield is a coroutine construct in Python that allows you to resume execution from exactly where you left it. So that's something we rely on here that emulates, in fact, backtracking in Python. Otherwise, you decompose the list of goals in G and G's here, and then you do the unfolding step. You get a list of new goals, and then recursively you yield from all the alternatives that this recursive call generates would be then forwarded again, and the code can resume at each time, and all that is beautiful and automatic in Prolog in Python, because Python has this yield coroutine construct. We will see that we can actually have it in Prolog if you want a little bit later. History of the implementation. Well, the efficient implementation is not this little interpreter, is the Warren abstract machine, uses registers, a stack for goals, and another one for close choices, and a heap and a trail. So one of the variants that you can look at if you are curious is a simplified form of it. Once you transform your code source into binary clauses by doing a continuation passing transformation. There are some nice alternative designs with stacks, also extension to high-log, which would allow you to have compound terms instead of function symbols. And all those are basically keeping the language first order is a translation mechanism. Some very nice indexing schemes originating from YAP and SWI Prolog. There is a TPLP issue dedicated to Prolog system implementation. At the end, I will show you all those citations for each of those things that I'm referring to. And then there is a very nice overview recently on Archive, which goes over the history of parallel implementation in full detail, and looks forward to the next step, maybe in a resurgence of parallel implementations. Some neat language constructs now in Prolog. Let's look at definite clause grammars. Definite clause is another name for or clauses, and then grammars made with them are definite clause grammars, or DCGs, abbreviation that everyone that plays with Prolog knows by now. But the DCG preprocessor, kind of a macro mechanism at read time, does is that it transforms spatial symbol arrow here. This is the first context-free grammar where the head is rewritten as a sequence of other symbols. It would just say that you can go from A0, that A0 can go from S0 to Sn if you go one little step with logic variable marking how far you go in the analysis or the synthesis of a sequence. So if you have this F is G and H, you get here F in out, G in to temporary, and then from the temporary one to out again. So the intermediate state gets chained in as many times as you need for those symbols. Now you can put curly brackets to call Prolog from any place in this execution mechanism, and then you can wrap non-terminals when there is no rewriting further down in square brackets, and that's it. That's definite clause grammars. So now let's look at a small toy problem. I called it DALI because there is an application that you will see in the next slides that's related to, well, not exactly what Salvatore Dali was doing, but close enough and crazy enough. So let's make a small generator of crazy sentences. Subject, verb, object. Subject is a cat or a dog. Verb is sitting. Adjective is golden or shiny. And an object can be on the adjective, somewhere location here, with you see the non-terminals and the terminals interleave nicely here, and then an instrument. Well, location will be the moon, the instrument is a violin or a trumpet. We run it, and we get some sentences like a cat sitting on the golden moon with a trumpet. Okay, well, the next thing is talk to a clone of the DALI AI program that is a recent very clever transformer-based algorithm that maps sentences in natural language, like a cat sitting on the golden moon with a trumpet, to images, billions of instances out there, learning from them, mixing them, and then the result of that is that you can see a cat sitting more or less on the moon with a trumpet. So go to this little site called crayon.com, I believe, with this spelling here, and enter your favorite sentences and change this little grammar to make you creative sentences as a small exercise. All right, procedural constructs in Prolog. Cat is needed to control search. We have seen some instances of it, and it can express things like if, then, else, and case constructs. There is a family of dynamic updates of the database: assert, retract, call a clause, abolish it. Basically a self-modifying program with its advantages and disadvantages. There is a backtrackable assignment of an argument, or non-backtrackable, very useful when you want to do library predicates with that. And of course, the impure constructs in Prolog should be used with moderation, but occasionally, especially for library developments, they are very useful. Okay, Prolog extensions with a bias for the road not taken. I stole that from Robert Frosty's poem. The guy goes on a path in a forest and then thinks about the other path and what would have happened if he took the other. We all face that kind of decisions in life. All right, so there is a common theme in some of the Prolog extensions, and especially their implementation, coroutining. So in constraint programming, what you do is you use attributed variables, so variables that have a little dictionary attached to them. And on that dictionary, you can put various things, including suspended goals. When unification gets more information for that specific variable, it's kind of a data flow mechanism, then unification could trigger resumption of some of the goals. And as a result of that, you can implement things like lazy streams and, in particular, lazy lists. Another Prolog extension that's very useful is tabling for expressing dynamic programming constructs. Goes well with well-behaved negation as failure, called SLDNF resolution, and XSB Prolog is the original host for tabling, but B Prolog and SWI Prolog have tabling at this time both. Parallel execution and parallelism, or parallelism, depending if you go along the body of a clause or you look at the alternative clauses. Nice algorithms, although in practice they didn't survive, partly because the granularity that they would impose on the execution mechanism is too fine. Might work on a dedicated hardware to actually do it right, including some GPU-based execution, but it's not widely used at this time in Prolog systems. On the other hand, multi-threading and remote execution and coordinations, they all could benefit from ability to save the state of the program, of course, and then resume it. So independent logic engines being first-hand objects, that's what will give a very useful coordination mechanism and, of course, a coroutine construct. So let's see how that works. Well, The best analogy is that of a programmer controlling Prolog's interactive top-level loop. You launch a new goal at the prompt, you ask for a new answer, then you look at it, you decide to go further or not. So it's basically an iterator over the stream of answers that's coming out. That could be finite or infinite. Logic engines could create other logic engines as well as interoperate with external objects, and then they could be controlled cooperatively or preemptively. This is the link to my emulation of engines with a slightly simpler language than the corresponding constructs in SWR Prolog, where this has actually been implemented. So now let's take a look at the API. You can create a new engine by giving an answer pattern and a goal, and you get a handle back. And you can share the code, of course, with the currently running program. And the answer pattern would be the one that will be bound with further instantiation of its variables, and a copy of that would be returned each time you do the next operation, which is asking an engine to return an answer instance. You can also stop an engine when you want, but what's important about this mechanism is that one can see this as transforming Prolog's backtracking over all answers into a deterministic stream of lazily generated answers. On backtracking, you cannot see the side that is not there anymore when you are on a next branch, next OR branch in the execution mechanism. But here you have full control on looking at what another engine would give at every step. Moreover, what you can do, you have also a yield operation, which allows you to give partially computed answers as answers of the engine. Anyway, in the resolution process, you can say, I'm yielding a term because I think it's interesting for my client to see it. And in particular, here you can say, I'm yielding an exception, and that would be a way to actually emulate a source level exception. SWI Prolog has a nice section on engines, and it's also documented. Let's look at some typical uses of an engine. You have a client, and you basically have the client ask for solutions, and the client can interpret the answer and then proceed to the next computation. So the process is fully reentrant, and the client may repeat it from an arbitrary point in its computation. What you can do with them, a lot of things on this slide. In particular, you can implement a source level Erlang style message passing with millions of engines. You don't need to map them to thread. You could if you want, but they are orthogonal to multi-threading. And then you can implement things like dynamic databases, source level, compose engines, have an algebra for that. First class logic engines have been added to this very little lightweight Prolog in Python interpreter. So if you want to see in a few lines how that looks, just go to this site, which is at my GitHub site, and go over the underlying. This is a Prolog with a simplified syntax at the same time. All right, so next, let's see how we can emulate Prolog's built-ins, and that's an introduction to them at the same time, with engines. Well, the if-then-else construct means making a new engine using the condition of the if as an answer pattern, get the answer back, stop the engine, you don't need it anymore, and then process the answer, look at, you get the condition back, and in that case, you propagate the bindings to the condition variable, and then you call the then part, right? That's what if then else does. And if the engine returns no, saying it didn't work for me, then you call the else part. So this is how you choose between the then and the else part by calling a condition on the engine. Okay, so you can emulate also negation as failure very simply. Once you have if, of course, if the goal succeeds, then fail, otherwise true. So you invert the failure and the success. Once if the goal succeeds, then return true, and then otherwise fail. Variable with a bunch of nested negations. So that's the negation here. With that variable is basically something that can be bound to two different things, but with not because you don't want the bindings to actually block the variable x as being 1 when you want also to try it with x equal to. Non-variable is just a negation of variable. You can emulate copy term, which is very useful to create a fresh instance of a term. And then you can, of course, emulate find all directly at source level. And it's reasonably fast, actually, to do so. When you have a good lightweight implementation of engines like the one in SWI Prolog. All right, here is some exercise with yield. That's a Fibonacci program that slices the window of two numbers by adding them up as you go. And then in the middle here, you yield them one at a time. So when you call the Fibonacci from outside, this is the client, you create a new engine. You don't care about the solution because it will never come out. This is an infinite loop here, but you collect the yields as they come and you repeat forever, and you ask one of the produced Fibonacci values. So it's equivalent to tabling and other things. It's an efficient Fibonacci program, almost like in a procedural language. You can do also find all. The one that we emulated works correctly. If then else works also correctly. Okay, now we get a little bit more serious. We will look at Prolog as a problem-solving tool. Well, let's look at Sudoku for kids first. So the Sudoku board can be represented with logic variables that we fill out here. And what we have here is that all these need to be different. All these need to be different. All these need to be different. And we express that separately for each row and for each column. That's the transposed of the matrix. And here we express by listing on each line the blocks, okay? So with this, we just want to say that all these actually permutations of 1, 2, 3, 4, right? And that applies to all of the components here. Well, let's then use something called map list that applies an operation to a list or more than a list, multiple lists, and gives you a result borrowed from Lisp long time ago. In fact, that's why the name map list persists in Prolog. And here is then a very simple solution. Assuming you have a permutation program, there is also a library one in SWI. Here is a one-liner for solving Sudoku, but kind of a one-liner. You fetch the board, which is a list of lists, and then the first one is what you want to return as an answer once you find the bindings, and you map list the map list of permutations of 1, 2, 3, 4 to each of the sublists. And here you have 3 S's to say it's a list of lists. That's my convention for marking multiplicity, and inherited from a book called The Art of Prolog by Sterling and Shapiro, which is very good one still and recommended. All right, so with that, we actually generate all the solutions for the Sudoku problem. And at the same time, if we want to solve one, we need to just replace the variables here with things that we know, and then the algorithm will find the others. Now, this is, of course, not the most efficient variant of Sudoku. So let's go for ages 13 and more. Well, for that, we transform an NP-complete problem, which is Sudoku, in fact, via a polynomial translation into a graph coloring problem, which is also NP-complete, but there are reasonably good algorithms for that. The same story happens with transforming, with a polynomial time transform to such solvers for planning, for instance. So let's see how that gets expressed here. So we have the full code, of course, for this link. Let me splash on it very quickly. So that's the complete code for the Sudoku problem. And we'll just outline some of the, let's say, more interesting steps in it. And there's some tests here to show that it solves, including for sizes up to 16. All right, let's see the key elements in this problem. So we have to turn to a difference graph board. We measure it, how big it is. We have a generator of index pairs I and j that locate any of those variables in the board. And then we call something that converts it to a different graph of differences, basically. So that's an adjacency list representation. For each of the logic variables, you have the neighbors that should be colored differently. Well, coloring in this case means have a permutation of all those things that need to be colored differently, right? So that they don't repeat, basically. So for that, you collect differences from the rows, from the columns, and also from the blocks. And then you concatenate them all together, and that would give you the set of all the differences that you have, all the difference constraints that you have. And then all you do is you apply them to your program, and that happens by defining first what it means to pick one of your neighbors that shouldn't have the same color as you. So whoops, the neighbors are variables, still unbound here. So you would make sure that you pick, that you take care of constants that have already been bound to values. And other than that, you just go through the adjacency list representation and make sure that you get bindings to the to each of the nodes in the graph that doesn't conflict with the bindings of its neighbors in any of those, again, rows, columns, or blocks in the Sudoku problem. And with that, you have a problem that, again, given Prolog's reversible nature, you get a problem solver. Escargot is one of the hard Sudoku problems, and then it solves it in less than a second. So significantly faster than the naive Sudoku for kids that I showed you before. So the program works up to sizes like 16 per 16, but it also works as a generator of Sudoku problems. You can also complete some of those things here and then generate a puzzle and, I don't know, publish it on an internet site with advertisements for people curious to solve more Sudoku problems. I never solved any of those, but I like writing programs that do that. It's a bit boring to solve Sudoku. All right, let's get to n-quiz as a pure horn-closed program. So the original idea comes from Tom Fruithirth. The way we would express this, well, on a chessboard, basically, you can express the diagonals as differences and other diagonals as sums of the positions of the queens. There is, by the way, a very nice paper by Wlodek Drabent in ICLP 22. Go and see a proof of correctness of this algorithm, okay? So I will not get into many details. I will just show it to you very succinctly here, given that you would read his paper and you will get a complete explanation and the proof of soundness and completeness for it. So what you will basically do, you will place it in a way that at each step, the position on the rows and on the two diagonals is consistent with the constraint, which says that the queens cannot hit each other right on the chessboard. All right, so I will then leave you with maybe the reading of the paper and playing with the code. Be amazed that it works with no arithmetics and it places the queens very nicely. Okay, the interesting thing about this program and well, the Sudoku problem as well is that they actually can be seen as filters on the set of all permutations of a given side. And because this problem doesn't really require numbers, I will show you here an execution with ABCD representing the queens. And what you would get as a solution is a permutation. So if ABCD represents the queen like this, the permutations that would come out would position them up or down on the columns of the board, okay? So you can think about 8 queens as a filtering algorithm on the set of all permutations. And the same story for Sudoku with a bit more variations on which those permutations would be. Well, let's get now to the final round, which is a few harder things, but well, hopefully with the expressiveness that Prolog provides, done easily. Start with lambda terms and De Bruijn indices. So De Bruijn indices provide a name-free representation of lambda terms. Terms that can be transformed by a renaming of variables or go in the same equivalence class. That operation is called alpha conversion, and the equivalence classes are alpha equivalence classes. So with the De Bruijn indices, variables have a nicer notation. You don't need to name variables, but you need to know how many steps you need to cross, how many other lambda binders you need to cross to get from your variable marked here unary notation as an integer, as a natural number actually, and depending on that you would get one of these lambda terms here. All of those 2 lambda terms would fall in this equivalence class. Read a bit more about De Bruijn indices if needed, but what is important about that is that you do not need to name variables to do lambda calculus with them. And actually, it's a bit easier. We'll also show that you will do with them some very nice other things like type inference in a minute. So lambda terms can be closed if all variables have a lambda binder, and if not, we call them open. Lambda terms are binary unary trees. All Prolog terms actually are trees, right? And the leaves in unary arithmetic marking distances to their lambda binders. So here the L marks a Lambda node, A marks an application node with 2 branches, and then an S node is a De Bruijn index in successor arithmetic again. So we don't use numbers in a conventional way here. We just use compound terms to express all these. And 0 is, of course, the leaf that terminates all those trees. So the language of the types now for Lambda terms, they're just binary trees. For those who program in Haskell, you can see that you have this type constructor. Haskell does type inference, by the way, and then variables in leaf positions will come out as types. And the code for all that, which is a bit more details than I will show you in the slides, is at this link. All right. Well, to test all our algorithms, let's look at something that Prolog is very good at, generating all terms of a given size. I found, very unfortunately, all right. Okay, let's put it down actually. All right, sorry for that interruption. Spamming happens. All right, so to generate the Lambda term, we'll either generate a variable which is marked with one of the n terms here in successor arithmetic. We have a Lambda binder that introduces the variables, and we have an application that applies the left side of the Lambda term to the right side. Now, when we want to have, this is the test showing them coming out, and what we have here is that at each step, when you generate either a Lambda constructor here or an application constructor, you would have price to pay for that. And I'm using successor arithmetic here. I will pay $2 for an application that has 2 parts, and I would pay one here for generating a Lambda binder. And with that, I can declaratively state it that I have n monetary units, and then the size of the term measured in based on this size definition here, 2 per application, 1 per Lambda binder, and 0 for a variable, that would generate me all the terms of a given size. All right. Same story for closed Lambda terms. And here it's getting a bit more interesting. I will have to make sure that every variable has a binder. So that means no undefined. If you look at the Lambda as a declaration of the variable, and then the variable referring to it as a reference, then it means that you would have no undefined variables in your Lambda term. Okay, those are closed terms. And for that, you just make sure that you have a list of variables above each of the leaves, and then that they are consumed by the variables when you hit one of the leaves. With that, you generate all the closed Lambda terms with this constraint. And they are fewer, of course, than the arbitrary ones or the open ones. So now, the next interesting thing is type inference. It's much simpler in Prolog than in any other language, in fact, partly because we have this unification with occurs check implemented at well, language level. So we do not need to implement it as you would need it in Haskell or Python. Let's look at what type inference actually means here. Well, for a lambda binder, you introduce a new variable here, and then you state the fact that its type, x arrow y, should be such that the type of the variable that you introduce here is added to the list of available types, and then y here would be then the type of the remaining expression, right? If the type of the body of the lambda expression is y, then because you introduce a new variable x here, a new variable here that has the type x, then that needs to be added to the list of variables to be eventually consumed by the leaves of your tree. When you have an application, you do the opposite. You actually say that a type of an application is y if you apply x, something of type x arrow y to something that starts with x here and ends up with y there. Okay, so that's something that actually reduces the type, and then lambda binders introduce or augment the type so that to fight against each other. Okay, what you want to state here as a constraint is that the type of a variable here in the tree and there in the tree, if they correspond to the same lambda binder, they have the same type. And types are compound terms, so you have to unify them to be sure that they are the same, and they could have loops otherwise. One of them could be a free variable, the other one containing the same free variable deep down. So you want to make sure that no cyclical terms are created, and then if that's the case, you will infer the type. So now we have the generators and we have the type inference mechanism at the same time. So what we can do is actually look at generating simply typable De Bruijn terms of a given size all in one. So you merge the two algorithms. One of them was the generator of the terms, and then the other one was the type inference algorithm. Now, if we merge them together, as soon as one of the constraints about wrong typing that is inferred as you generate the term fails, then you give up on that generation. So you would have a very, very fast generator for simply typed lambda terms by doing that. So this is basically then the merging of the whoops, I tapped on the wrong key here. We'll recover in a second. Further down, here we go. One more step, a few more steps here, and the De Bruijn indices. And this is then the generator for closed terms. This is in fact merged with the type inferencer here. Merging is happening by just kind of putting all the arguments of the two of them as part of a bigger predicate, what you see here, and sharing what can be shared between them. So with that, you get then a generator for simply typed terms of a given size. One of the things you will see in a minute about those is how we can use them to teach a deep learning system to do theorem proving, which is hard, even for humans, right? Infer a lambda term that would have a given type is much harder than doing type inference. It's actually p-space complete. We'll see that. So here are just some examples. So I have a generator for terms, well-typed terms of size 4. And here is the type expression. Here is the lambda term. Here is something with an application. And these are De Bruijn indices. for them, and you can try it out for larger ones. There is an entry in the encyclopedia of integer sequences that counts how many of these are up to a given size, but there is no close formula to count them. All right. So the next exercise is to write a theorem prover in intuitionistic logic. So let's see how we do that. A theorem prover for intuitionistic propositional logic in Prolog, actually. That's what I meant. The code is, again, one click away here. Why intuitionistic logic is interesting, while it's used in today's proof assistance. There is a correspondence between computations and proof, the so-called Curry-Howard isomorphism, which connects the implicational fragment of propositional logic with seen as types with the simply typed lambda calculus, right? So formulas in the logic and types in as types of lambda terms in the lambda calculus behave isomorphically, partly because their axioms, if you use combinators, kind of look the same as well, the Hilbert-style axioms in propositional logic. So few steps to get there, but it's a very nice correspondence. So type inference now computes the type of a lambda term, which is a theorem in intuitionistic propositional logic. Now a theorem prover solves the harder piecewise complete inverse problem of finding a proof given a formula representing a type. A simply typed lambda term can be synthesized as a result of a successful proof of, for the implicational subset. Let's now look for how you would build a theorem prover for this logic, actually for the more general logic that has not just implications, but also the other connectives. Sequent calculus that people use to formalize virtually all interesting logic formalisms can be almost naturally transliterated to Prolog, provided that you go from the conclusion to the premises. So the conclusion would become the head of the clause, and the independent premises here would be the conjuncts in the body of a Horn clause. So that's the general idea how you turn sequent calculus into Prolog code. Of course, there are some glitches that could happen, but sequent calculus doesn't guarantee you that if you apply those rules in the wrong order, you will have termination. So the nice thing about this particular formalism, which is called G4IP, brought to us by Roy Dykov, but known in the past also by Vorobiev, a Russian logician in the, I guess, in the 50s, is very nice because you have a natural multiset ordering that can be used to prove termination. And the key rule is here. Here is the interesting, tricky implication, which is an implication implying something, okay? And that can be broken into smaller parts, smaller implications here. And with that, you actually progressively, you reduce the complexity of the formulas, given a good definition of the complexity, and you can prove termination. So that's what we'll use. We'll get the intuitionistic theorem prover here as being, again, a transliteration of those rules going from the conclusion to the premise of the sequent. Step by step for all of them, what we have a bit more than in that calculus here, we also handle double implication because that shows quickly that two formulas are equivalent. So you can prove tautologies with that if you want, with the two different parts are the same, right? And for those used with Prolog, we put implications backwards, actually. Inverse implication can be also one of the operators. Otherwise, you have conjunction and disjunction and negation here, and they all need to be handled. Negation is something that implies false, is a definition of negation in either intuitionistic or classical logic. So you delegate the reduction mechanism a bit further down, and you will have the handling of the more complicated rules, the breaking the rule that I just mentioned, that needs to be simplified to get the termination property handled, delegated to those two predicates. One of the nice consequences of that is via the translation from of classical logic into intuitionistic logic via Glivenko's theorem, is that if you apply double negation to a formula T here, and it's intuitionistically provable as such, that means that the original formula without double negation is provable classically. So you can get a classical logic prover for free, but there are much faster ones for classical logic. For intuitionistic logic, this is a pretty good one anyway. Here are some examples of execution of some of the rules. You can see, for instance, that classical logic likes P or non-P as being true, and intuitionistic logic doesn't like that. Triple negation is the same as single negation in intuitionistic logic, and a few other examples, including some nice equivalences. This one here is useful for a Horn clause reading of a formula. The head is the conjunction of BCD if is the iterated implication with left associativity here of the head by B and C and D. Okay, well, let's go one further step now with an application of this story, right? We could train neural networks as theorem provers, provided that we feed them with enough data. So for that, we need to have a generator of formulas. And because of the Curry-Howard isomorphism, what we do, we will pick formulas that come as types of lambda terms, right? They're actually lambda terms in normal form, which is one step further. But what we do here, we have a almost linear type inference algorithm and generation of the formulas. But now we read them backwards. We read them from the theorem on the right as being the input to the neural net, and we would like the proof term, which is a lambda term, that would be the one that if the theorem prover can find it, it's not just telling you that this is a theorem or not, so it's not just a classification problem, but it actually tells you why it is so by giving you the proof. So this can be also extended a bit to further down to full fragments of the logics, but let's just look at how we do it with machine learning very quickly. So we have usually training, validation, and test sets. We do not want to overfit, and we do not want, we cannot do much on completely random terms in terms of machine learning. The algorithm that we would adopt here would be sec to sec. So we'll represent our formula as a tree in a, let's say, postfix notation. We'll do the same thing for the lambda term, And then we have two sequences. It's almost like a translation from English to French, okay, or from, from some form of code to some other form of code. You would like to train on a very large data set which we would generate. So we have now the choice of neural networks and a little bit of a justification of why we do that. We have the easier case first, which is linear implication. Well, each lambda term corresponds to a single variable. Each binder corresponds to a single variable. And then linear implication would provide the type for such terms. Linear logic has this lollipop operation for it. Here is a very simple example, which the formula and its type look almost the same. We will see how well learning works on that. And after that, we'll go to the same problem for the p-space complete problem. This is polynomial to go from here to there, but for the implication of fragment of intuitionistic propositional logic, it is p-space complete to find the proof for it, materialized eventually as a lambda term. So that's the story of what kind of sec-to-sec algorithm we choose. This can be also replaced with transformers, which work better, especially if you feed them with a very large amount of data. And instead of having our postfix representations, you can also consider things like embeddings, like people use in natural language processing, basically a vectorization of each of the terms. But we pick LSTM networks that do reasonably good on sec-to-sec translations. It's a form of recurrent neural network that kind of slides a window and keeps information from the previous layer when you stack them in the deep learning network. So how the performance looks for that? Well, you can take a look at my types and proof site on GitHub and see a little bit some of those examples with various forms of neural networks and generators and the complete code, actually. But there are also some data sets that I translated to Prolog that can be tested with other tools, comparable ASP or anything else that would work on those logic formulas could be seen as an alternative implementation. So here's the beautiful accuracy curve hitting close to 100 on linear logic, which is the easy subset. This is the loss function that goes down. That's a good thing when you evaluate neural networks. This is, again, the accuracy curve going up, and the loss curve for, again, the linear subset plus unprovable formula. So we have here accuracy on provable and unprovable ones. You have to distinguish between the two and do it successfully. And now the question is, can we do it for the general case, arbitrary propositional logic? You get very good accuracy, but not perfect one this time. And there are some surprising gaps in the loss function here, as well as in the actual learning curve for that. But the performance is still very close to 100%. So it's going quite well. So it shows that with this trick, the Curry-Howard isomorphism, you can actually train theorem prover on a difficult p-space complete logic quite effectively. All right, our conclusions now. We have shown you some of the strengths of Prolog with focus on problem solving, including some harder ones, but we stayed with the whole clause logic kernel. As a highlight, we started with a two-line meta-interpreter, and we captured the necessary step-by-step transformation that one needs to implement Prolog in a procedural language that mimics this meta-interpreter. And we showed you some snippets in Python, and there is actually a complete implementation in Python that covers it. Some suggested further explorations going beyond Prolog, even historically, while constraint solving extensions are very nice. Tabling is very useful, and then variants like probabilistic logic programming bring us closer to this very important next research topic, which is neurosymbolic extensions to Prolog and synergies with machine learning in general and natural language processing in particular. So some resources, very nice online book by Mariusz Striska here. Of course, The Art of Prolog, good classic. Several Prolog implementations listed here. And then, of course, more of that in the Prolog Wikipedia article. And here are some of our references marked with corresponding numbers in the slides. You can go and see them for some of the details that we covered in the text. So this is the talk. I don't know if I went overflow because of the spam that interrupted me watching the clock on my phone. Thank you for listening, and ready for questions that would be, well, not face-to-face, but interactive. Thank you.